Hello class 12, this is another video regarding semiconductors. Now we've already checked the band theory of solids, okay. So this is that for an insulator, the band diagram for energy band diagram for an insulator, and you can see there is a huge band gap of about 7 electron volts between the valence band and the conduction band in case of insulators. In case of semiconductors, the band gap is there, but it is much lesser compared to that in case of insulators. And there is of course a gap between the valence band and the conduction band. This is also called the forbidden band or forbidden energy gap. Do not forget that. So the band gap in case of semiconductors is in the range of like about 1.1 electron volts, and in case of conductors there is no band gap, so to say, between valence band and conduction band, such that the electrons in the valence band can easily jump or go to the conduction band, no problem whatsoever in case of conductors. So when the electrons reaches the conduction band, they become free electrons, and thereby these free electrons help in the conduction of electricity. Okay, so that is the case. All right. So in case of germanium, the band gap energy is like 0.72 electron volts. In case of silicon, it is 1.1 electron volts. You will get to draw these pictures in the exam, remember. For energy band theory, from energy band theorem, you will get to draw these pictures in case of insulators, in case of semiconductors, in case of conductors. All right. Now coming to semiconductors, first of all, let us talk about the kinds of semiconductors. Basically, the semiconductors can be differentiated, can be divided into two groups. One is called intrinsic semiconductor and the other is called extrinsic semiconductor. Now, what is an intrinsic semiconductor? Semiconductor in its purest form that we get, readily available is what is called, intrinsic semiconductors. Now, in nature, we get two semiconductors, which are silicon and germanium. There are other kinds of semiconductors also which can be generated, like, which can be made like an alloy. Okay, like gallium arsenide, gallium phosphide are some, semiconductors that can be made. Now, in nature, the semiconductors that we get in its purest form is what is called intrinsic semiconductor. So to say, there are no impurities or any other atoms of any other element are not doped inside this intrinsic semiconductor. We are going to see what that doped actually means. Now, extrinsic semiconductor is impure form of semiconductor. Okay, in extrinsic semiconductor, what happens is we have added in, say, silicon or germanium, that the semiconductors that we get in nature. So these that we get in nature will be intrinsic semiconductor in its purest form. Now, in these intrinsic semiconductor, if we mix some atoms of some other elements like aluminium, phosphorus, arsenic, boron, okay, we can add atoms of different elements like aluminium, like I said, phosphorus, boron, okay, into these intrinsic semiconductors, purest form of semiconductors. The semiconductor that we then get is what is called extrinsic semiconductors. And it is extrinsic semiconductors which has wide usage, which actually has revolutionized the world. The impure form of semiconductor is what has revolutionized the world. We are going to talk about that later. And this process, by the way, of mixing the atom of some other element like aluminium, phosphorus, boron, arsenic, okay, into these intrinsic semiconductors, that process is what is called doping. It's like we are injecting those atoms of different elements into these intrinsic semiconductors. That process is what is called doping, remember. All right, now here what we have is electronic configuration shown, that of silicon and germanium. Silicon has atomic number 14 and germanium has atomic number 32. So this is the electronic configuration like. And therefore, what we get to see is the valency of semiconductors, silicon and germanium, and also that of alloys, gallium arsenide, gallium phosphide that we get. Okay, the valency will be 4. So the valency of silicon, 3s2, 3p2, this is the valency. This gives the valency of silicon, and this gives the valency of your germanium. All right. Now, what is the atomic structure, like in case of an intrinsic semiconductor? Here I have given the example of silicon. This very thing is true for germanium also. And what we've done over here is, so we've only shown the valence electrons of the, semiconductor atom. So there are 5 atoms that I have shown in here, and the valency is 4, means there are 4 electrons on each of the atoms. what happens is these different atoms are bound to each other by sharing of electrons, and this sharing of electrons is what is called covalency. Okay, so what is true is, in case of semiconductor, in case of an intrinsic semiconductor, what happens is the atoms are bound to each other through covalent bonds. Okay, so mutual sharing of electrons happens, and thereby these atoms are bound to each other through this covalent bonds. Now, like we've already discussed in extrinsic semiconductor, what happens is the intrinsic semiconductor, this thing itself, okay, this is how the atoms are bound to each other in intrinsic semiconductor. Now, in this intrinsic semiconductor, so we have a material of the semiconductor that we get. Okay, now inside this material there are different atoms, and each of these atoms are bound to each other through covalent bonds. Now, in this material of the semiconductor, what happens is, to make the semiconductor, to increase its application, so what happens is, to increase its usage, what happens is we actually or inject atoms of other elements like antimony, bismuth, phosphorus, aluminium, boron, gallium, okay, arsenic, of course. So we inject atoms of these elements in the intrinsic semiconductor, okay, and that is what is called your extrinsic semiconductor. Remember, now extrinsic semiconductor itself can be of two kinds. One is called n-type semiconductor. Now, in n-type semiconductor, what happens is, in the intrinsic semiconductor itself, we dope in pentavalent impurities, or atoms having valency 5. Penta means 5. Okay, so examples like arsenic, antimony, bismuth, phosphorus. So we inject the atoms of arsenic, antimony, bismuth, or phosphorus inside the material of the intrinsic semiconductor, inside the material of the intrinsic semiconductor itself. So when we dope in pentavalent impurities like this in an intrinsic semiconductor, the semiconductor that we get is called n-type semiconductor. Why it's called n-type, we are going to see that. Also, what we can do is, in an intrinsic semiconductor, we can dope in atoms of elements having valency 3, like aluminium, boron, gallium. So when we dope in trivalent impurities in an intrinsic semiconductor, what we get is a p-type semiconductor. Why it's called p-type, we again are going to look into that. Okay, we are going to talk about this also later. Now first, let us see what happens in an n-type semiconductor, how the atoms in n-type semiconductors are now bound. Let us look into that. So in intrinsic semiconductor, this was the case, like covalency. Okay, so silicon atoms are bound to each other. The same is true for germanium also, remember. Now we have, in n-type semiconductor, we dope in pentavalent impurities, as you can see over here. N-type semiconductor, pentavalent impurities we dope in. So say I'm giving an example of arsenic. So you have an atom of arsenic doped in, and you have nearby silicon atoms. Now what happens is, these atoms are bound to each other again by sharing of electrons. This is called covalency, as you already know. But in the process, what happens is, since we've doped in pentavalent impurity, there is an excess of an electron, as you can see in here. So there are other arsenic atoms also which are doped into the intrinsic semiconductor itself. So what we are in turn getting is, we are getting, for every covalent bond this way that is formed when a pentavalent impurity is doped in, we are getting an excess of electrons. And these are valence electrons, of course, that we have only depicted in the picture. So these electrons, being valence electrons, they can easily jump out of their orbit and become free electrons, which eventually help in the in carrying electric current. So these things help in the conduction of electricity, so to say. Now, since we have an excess of electrons in case of n-type semiconductors where pentavalent impurities are doped in, so therefore electrons now being negatively charged, therefore these kind of extrinsic semiconductors are called n-type semiconductors. And as you can see written here, in n-type semiconductor, the majority charge carriers are electrons. Why? Because we are getting excess of electrons, and these electrons help in carrying electricity. So therefore we say majority charge carriers. These are in major numbers. Now we have an excess of electrons now. So therefore, they are the majority charge carriers, which are called electrons. Which are electrons, of course, and this type of semiconductor is called N-type semiconductor. Likewise, let us see what happens in P-type semiconductor. In P-type semiconductor, we have doped in trivalent impurity. As you can see, I've given an example of aluminium. So here also sharing of electrons happens. The atoms are bound to each other by sharing of electrons. But in turn, in the process, what we see is, for this electron to form a pair, there isn't an electron. So to say, here we have a deficiency of electrons. Okay, so there is a gap over here. There's a hole over here, so to say. This hole was supposed to be filled up by an electron so that a covalent bond could be formed. But since we have a deficiency of electrons, that deficiency of electrons is given a name. It is called a hole itself. All right. Now, there are other aluminum atoms also that are doped into the intrinsic semiconductor. Now, since due to this trivalent impurity that is doped in, we have an excess of holes. So therefore, this kind of an extrinsic semiconductor is called P-type semiconductor, because this is the hole is the deficiency of electron, which is negatively charged. So deficiency of electron, that is negatively charged electrons, means it's like you have a positive charge over here, because the negative charge supposed to be here is not here. So negative charge is absent, means it's like positive charge is present. So these things are actually called holes, and we consider these holes to be positive charge carriers. Why? Because this hole, to fill up this hole, an electron, say for example, can jump this way, this electron can come and fill up the space over here. Now when this electron jumps over here, what happens is there's a deficiency of electron created here. So a hole is generated here. Now this hole is filled up by another electron coming. Okay, so again, when this electron comes and fills up this hole, there is another hole that is generated in here. So electrons are coming this way, as you can see, in the downward direction. So electrons are moving in the downward direction in my example. So it's like saying the holes are moving in the opposite direction, because you can see electrons are jumping downward, holes are moving upward. And since electrons being negatively charged, negative charges are moving in the downward direction, means it's like saying positive charges are moving in the upward direction. So therefore, holes are considered to be positive charge carriers. Remember, electrons are negative charge carriers. So since in P-type semiconductors, holes are in excess, so to say, so therefore, or positive charge carriers are in excess, therefore these are called P-type semiconductors. This kind of an extrinsic semiconductor is called P-type semiconductor. So in P-type semiconductor, we have majority charge carriers to be holes, which we consider to be positively charged. And in N-type semiconductor, majority charge carriers are electrons, which of course, as you all know, are negatively charged. So this is about N-type semiconductors and P-type semiconductors. Now let us look into what is called a Pn junction. Okay, now comes the real important things for you all. Say we have initially an intrinsic semiconductor. So this is an intrinsic semiconductor, or semiconductor in its purest form, could be silicon, germanium, or some alloys. Okay, now what happens is, one side or one end of the semiconductor of this intrinsic semiconductor is doped in with trivalent impurities, such that on one side you get an excess of holes. Okay, and the other side, what you do is you dope in with pentavalent impurities, such that on the other side you get an excess of electrons. So holes are denoted by this sign, and electrons by simply a circle C. So these are electrons. So what happens is, this intrinsic semiconductor, one side of the intrinsic semiconductor, now this is actually no longer an intrinsic semiconductor. This itself is an extrinsic semiconductor actually, because we have doped in impurities. So this side of the semiconductor, since it has excess of holes, becomes the P-type semiconductor, and the other side of the semiconductor being doped in with electrons becomes the N-type semiconductor. Now of course there is a junction between the P-type and the N-type semiconductor. This junction is what is called the Pn junction, the junction between the P-type semiconductor and the n-type semiconductor is what is called the Pn junction. All right. Now, of course, it's not like, you take one intrinsic semiconductor, dope in with trivalent impurities such that this becomes P-type, and then you take another intrinsic semiconductor, dope in with pentavalent impurities such that this becomes N-type, and you fix them with Fevicol or, super glue or something like that. You paste them together. It's not like that. Okay, so Pn junction is formed by taking one solid intrinsic semiconductor, doping one end with trivalent impurities such that one side becomes P-type and the other side become being doped with pentavalent impurities such that the other side becomes N-type semiconductor, remember. So this is Pn junction. This is how it is formed. Okay, now what happens in Pn junction? Now this is the Pn junction like we said, and we know unlike charges they attract. So what happens is, the electrons that are very close to the junction, you have to understand this carefully. The electrons that are close to the junction, they simply jump to the other side. These electrons, they simply jump to the other side just to fill up these holes. As you can see here, the holes are filled up now, very close to the junction. So this is the junction, Pn junction. Now since the electrons have very close to the Pn junction from the N-type side, or from the N side simply, they've jumped to the P side, there is a deficiency of electrons that has, been formed here, very close to the junction on the N side. Okay, so what happens is, you have holes formed in here and you have electrons on the P side here, very close to the junction. Now these electrons also, on the other side of the N-type, these electrons also want to jump to the other side actually, but these electrons are prohibited from jumping or through this Pn junction by these electrons. These electrons, they repel these electrons which also want to jump to the P side. Okay, so what happens is, there is this new region formed on either side of the Pn junction. So this is a Pn junction. So there's a region formed on either side of the Pn junction, and you can see this region is actually depleted or deficient of the majority charge carriers on either side. What I mean to say is, on the P side, we know the holes are the majority charge carriers. We've seen that the holes are the majority charge carriers on the P side. But just very close to the junction, Pn junction, in this region of space, okay, on the P side actually, this is supposed to be holes, majority charge carriers, but this region on the P side is depleted of holes, which are its majority charge carriers, because now you have electrons in here. Likewise, on the N side, the electrons are the majority charge carriers, but this region is now depleted of the majority charge carriers electrons, and you have holes in here. Okay, so since this region on either side of the Pn junction is depleted of the majority charge carriers, therefore this region is what is called the depletion region, or also called the potential barrier. It's like a wall, barrier. Okay, why is it called potential barrier? Because holes, we said, are positively charged and electrons are negatively charged. So you have a potential or electric field generated in here. Okay, electric field lines are from positive charges to negative charges. This is what we have learned in electrostatics. So there's a potential difference generated. This is P side, positive side, this is positive, and this is negative. So there's a potential difference generated in here. Therefore, and why is it called a barrier? Because like I said, electrons are not allowed to jump through the Pn junction by these electrons now. Likewise, you can also understand it this way. The holes are not allowed to jump through the Pn junction by these holes. They repel. Alright, so this region, therefore, it is also called the potential barrier. Okay, for these electrons to jump to the other side, they have to overcome the potential barrier. They have to gain enough energy so that they can overcome the potential barrier and thereby jump to the other side. Only then they can jump to the other side. So since, like I said, this region being depleted of the majority charge carriers on either side, therefore it is called the depletion region. This is a completely new concept for you all, that of depletion region, and of course the concept of holes, which are positive charge carriers. Okay, this is a completely new concept for you all. So please try to understand this clearly, and if you don't understand, you can revise this video and check that again. So since the region on either side of the p-n junction, that is what I've written here, is depleted of the majority charge carriers, so it is called the depletion region. So you might be asked, what is depletion region? Okay, so you have to write this. Okay, and this region, only this region is called the depletion region. And by the way, I forgot to tell you one thing in the video. So n-type semiconductors, we said the majority charge carriers are electrons. Now since we have a majority, we will have a minority also. So in n-type semiconductors, minority charge carriers are holes. Majority charge carriers in n-type are electrons, since we have excess of electrons. So majority is electrons, minority is holes. Likewise, in p-type semiconductors, we have excess of holes. So majority charge carriers are holes, minority charge carriers are electrons. Please do not forget this. So this is about the p-n junction and the depletion region. Very, very important concept for you all, that of depletion region. Now what we are going to talk about is something called the Pn Junction Diode now. Okay, this is the thing that has wide applications, that actually has revolutionized the world.